Hello everyone. Welcome to the 17th lecture on topology. In this lecture, we'll discuss about connected spaces. Let X be a topological space. A separation of X is a pair of disjoint non-empty open sets U and V in X such that union of U and V is equal to X. That means if we have a topological space X, then we say that X has a separation if there exist two non-empty disjoint open sets U and V whose union is equal to X. A space X is said to be connected if there doesn't exist any separation on X. A space is said to be connected if there doesn't exist a separation of X. So what is a separation? Suppose we have a space X here. This space X has a separation if there exist two disjoint non-empty open sets U and V such that U union V is equal to whole X. If U union V is equal to X is a separation of X, then U doesn't contain any limit point of V. How? If we take any point outside V, that means if you take a point in U, then that point cannot be a limit point of V because U itself is open, and so we have an open set U containing that point which doesn't intersect V. So any point in U cannot be a limit point of V. Similarly, any point in V cannot be a limit point of U. That means closure of U intersection V is empty. Similarly, closure of V intersection U is empty. Closure of U intersection V is empty because we know that closure of U is U along with all its limit points. Here we have seen that V doesn't contain a limit point of U. That means U contains all its limit points inside it. So U along with all its limit point means U itself. That means closure of U is inside U. So closure of U intersection V is empty. Similarly, closure of V intersection U is also empty. Now let us take this example. Let X be a 3-point set ABC and tau be the collection of subsets of X as whole space X, empty set, set containing 2-point AB, set containing 2 points BC and the singleton set B. Clearly this is a topology. So this X tau is a topological space. Now let us check whether this topological space is connected or not. In this space, there doesn't exist two non-empty disjoint open sets U and V such that U union V is equal to X. Because here we can see that here we have an open set AB and another open set BC whose union is X, but these two open sets are not disjoint. And we cannot find two non-empty disjoint open sets whose union is the whole space. So in this case, there doesn't exist any separation on X. So the space is connected because we know that a space is connected if there doesn't exist any separation. Take one more example. Let X is equal to ABCD with the topology tau, which contains X, empty set, A, B, set containing AB, set containing CD, set containing ACD, and set containing BCD. Now let us check whether this topological space is connected or not. Let us take two sets U is equal to AB and V is equal to CD. Clearly this U and V are open sets. AB and CD are open here. So U and V are two open sets which are non-empty and they are disjoint. And we can see here that U union V is whole space. Therefore, there exists a separation on this topological space. So the space is not connected. A space X is connected if and only if the empty set and the whole space are the only subsets of X that are both open and closed in X. Let us prove this. Let U be a non-empty proper subset of X, which is both open and closed in X. Let V is equal to complement of U. Since U is closed in X, complement of U is open in X. So our V is open. Here we have taken U as a non-empty proper subset of X, which is both open and closed. Now here we have V, which is open in X. Since V is complement of U, if we take U union V, that is our whole space. So here we have two disjoint open subsets U and V of X such that U union V is equal to X, which is a contradiction to the fact that X is connected, because here we have a separation. If U is a non-empty proper subset of X which is both open and closed, then we have a contradiction here that X is not connected. So our assumption that U is both open and closed is wrong. So there doesn't exist any non-empty proper subset of X which is both open and closed. So we can say that the only both open and closed subsets of X are empty set and X itself. Now here we have another example. Let X be an infinite set with cofinite topology. That means tau is the collection of all subsets U of X such that complement of U is either finite or all of X. We have seen in our earlier lectures that in such type of spaces, X be any infinite set with cofinite topology, then there doesn't exist two disjoint open sets. So in this topological space, we cannot find two disjoint open set. So the space is connected. We cannot have a separation in the cofinite topology. Any set with discrete topology is not connected, because in case of discrete topology, every subset is open. So if we take any proper subset of X, then that is open, and the complement of that open set is also a subset of X, so that is also open. If we take the set and its complement, which are both open and disjoint, but their union becomes the whole space, so we have a separation. So any set with discrete topology is not connected. Any set with indiscrete topology is connected, because in indiscrete topology the only subsets which are open are whole space and empty set. So we cannot find two non-empty proper subsets of X. We cannot find two non-empty proper open subsets of X whose union is whole space. So the space is connected because we don't have a separation in case of a set having indiscrete topology. Real line with standard topology or usual topology is connected, because in real line with standard topology, we know that the open sets in real line with standard topology is either open intervals or union of open interval. So in case of real line, we cannot find two disjoint open intervals whose union is the real line. We cannot find two disjoint open intervals in real line whose union is R itself. So we cannot have a separation in case of real line. So real line with standard topology is always connected. Let us consider the set of rational numbers, Q. Here we have to consider Q as a subspace of real line with standard topology. And let us check whether this set of rational numbers are connected or not. In real line, let us choose a irrational number P. Now these two open intervals, minus infinity to P and P to infinity, are two disjoint open sets in R, because R is having usual topology. These two open intervals, minus infinity to P, where P is a irrational number, and the interval P to infinity are two disjoint open sets in R. Since we are considering the set of rationals Q as a subspace of R minus infinity to P intersection Q. Let us name it as U is open in the subspace topology of Q. Similarly, P infinity intersection Q. Let us name it as V. This is also open in the subspace. So here this U and V are two disjoint open sets in the subspace Q. And if we take the union of U and V, we'll have our rational numbers. Clearly this U and V are two disjoint non-empty open sets in Q such that U union V is equal to Q. Therefore Q has a separation. Hence Q is not connected. Let us take this theorem. Let Y be a connected subspace of Y. If the set U and V form a separation of X, then Y lies entirely within either U or in V. If Y is connected subspace of X and X is having a separation, Y is connected and Y is a subset of X, whereas X is having a separation, X is equal to U union V. Then this connected subset entirely lies either in U or in V. Let us prove it. If the sets U and V form a separation of X, then U and V are two disjoint open sets in X such that U union V is equal to X. As Y is a subspace of X, U intersection Y and V intersection Y are two disjoint open sets of Y. Since U and V are open sets in X, so U intersection Y and V intersection Y are two disjoint open sets of the subspace Y, such that U intersection Y union V intersection Y is equal to whole space. If both U intersection Y and V intersection Y are non-empty, then there is a separation in Y, which is a contradiction to the fact that Y is connected. Since Y is connected, one of these U intersection Y or V intersection Y has to be 0. Because Y is connected and here we are getting a contradiction that U intersection Y, V intersection Y forms a separation for Y. So one of these two, U intersection Y either is empty or V intersection Y is empty. If U intersection Y is empty, then Y completely lies in V. Here U intersection Y is empty. That means Y is not intersecting U. Therefore, Y is completely lies inside V. Because Y is a subset of X and X is having separation U union V, and this Y doesn't intersect U, so Y must be a subset of V only. Similarly, if V intersection Y is empty, Y completely lies within U because Y is a subset of X and X is equal to U union V and Y doesn't intersect V. So Y is a subset of U. Let us prove this theorem. Let X be a topological space and C be a connected subspace of X. If C is a subset of D, which is a subset of closure of C, then D is also connected. That means if X is a topological space and C is a connected subspace of X, if D lies inside in between C and closure of C, then D is also connected. We have to prove this. Let C be a connected subspace of X and let C is a subset of D and D is a subset of closure of C. We have to prove D is connected. Let us assume that D is not connected. If D is not connected, that means D is having a separation. Let D is equal to U union V with the separation of D. That means U and V are two disjoint non-empty open subsets of D and D is equal to U union V. Since C is connected, and C is a subset of D. Here we have C is a subset of D. Since C is connected and C is a subset of D, by the previous result, C entirely lies either in U or in V. Because in the previous result, we have seen that if Y is a connected subspace of X and X is having a separation U union V, then Y either lies completely inside U or within V. Similarly, here C is a connected space and C is a subset of D and D is having a separation U union V. So C either lies in U or C lies in V. Let C is a subset of U. This implies closure of C is a subset of closure of U. This implies closure of C intersection V is empty because closure of U intersection V is empty. We have seen this. If U and V forms a separation, then U doesn't contain any limit point of V and V doesn't contain any limit point of U. So closure of U intersection V is empty. Since closure of U intersection V is empty, closure of U intersection V is empty and closure of C is a subset of closure of U, closure of C intersection V is also empty. This implies D intersection V is empty because closure of C intersection V is empty and D is a subset of closure of C. So D intersection V is also empty. This implies V is empty, which is a contradiction to the fact that V is non-empty because D is equal to U union V is a separation of D. So U and V are non-empty. Here we have V is empty, which is a contradiction. Therefore, D is connected. If V is empty, that means we cannot write D is equal to U union V, whereas U and V are two disjoint non-empty open subsets. Therefore, D is connected. So what we have seen here, if X is a topological space and C is a connected subspace of X, if D lies in between C and closure of C, then D has to be connected. Now in this theorem, we'll prove that image of a connected space under a continuous map is connected. Let X and Y be two topological spaces in which X is connected. Let F be a mapping, continuous mapping from X to Y. We have to prove that image of this X under the continuous map F is connected. That means we have to prove F of X is connected. Let us assume that F of X is not connected. Suppose F of X is not connected. That means F of X has a separation. Let F of X is equal to U union V be the separation. Since F is continuous, F inverse U and F inverse B are two disjoint non-empty open sets in X such that X is equal to F inverse U union F inverse B. Because F is continuous and U is open, we know that inverse image of every open set is open if F is continuous. So F inverse U is open, F inverse B is also open. These F inverse U and F inverse B are open subsets of X. They are disjoint and their union is X. So X is having a separation here. This is a contradiction. We have X as a connected space and here we got that X has a separation. So we have a contradiction. So our assumption is wrong. We have assumed here that Fx is not connected. Therefore, Fx is connected. This is all about in this lecture. In the next lecture, we'll study about some variants of connectedness, that is locally connectedness and path connectedness.